Okay, so hello there. In this chapter, we're talking about populations and sampling. This is the sampling chapter. And so let's get started. So an overview of what the lecture will cover. We're going to look at what sampling is, the concept of probability, taking a simple random sample, and then how similar the sample is to the population, as well as some practice problems. So first, population versus sample. So a population refers to all of the cases or people that you're interested in studying for your research. Those could be individual people, it could be businesses, it could be groups of people like schools or neighborhoods or different states in the country. But it's all of the people that you're interested in studying, the universe of cases. And a sample is a subset from the population. So you, the researcher, choose a small number of people from the population that you're going to study. That could be a small number of people. It could be a small number of schools or a small number of neighborhoods in Los Angeles or a small number of states in the country. But you, the researcher, choose your sample. Why not just study the whole population? And usually researchers are not able to study the whole population because it simply will take too long to do so. The population's too big, or it would just be too hard, or it could be too expensive. Researchers don't have an unlimited budget. Everybody, has a bottom line that they have to meet. And often studying the whole population is just really, really expensive. And it's not possible with the budget that you have. And then in some cases, it's really impossible to survey the entire population. So there's a lot of reasons why researchers don't study the whole population. So in statistics, what I want you to remember is when we use the word population, we are not talking about the population of everybody in the United States, right? That is not what population refers to. Out in the pop culture, when people are talking about, oh, the population, they're referring to everybody living in the United States. But in statistics, the term population does not mean the same thing. So the population is the universe of cases that you're interested in studying based on whatever your research question is. And so your cases could be CSUN students, they could be schools, neighborhoods, states. And so if it was CSUN students that you were interested in studying, then that's your population, all of the students at CSUN. And a sample would be taking, a subset of, I don't know, a couple hundred or a couple thousand CSUN students. So what is the purpose of taking a sample? We can learn a lot about the population if we carefully take a sample of it. And we use the data from our sample to generalize about the characteristics of the much larger population. This is the basis of all inferential statistics. That is that we're making predictions about the population based on data from our sample. The survey that we've been using in class, in the lab, the General Social Survey, that is a sample of adults living in the United States. So we're using data from that GSS sample to generalize or to infer about the characteristics of adults in the United States. And so that's why we're using the GSS. We can do inferential statistics with it. And so here's a good little graphic of population versus sample. This is what we're interested in. If this is our full population, we're interested in all of these folks, right? And so we're going to take a sample from that population. And this is an example of what our sample would look like. So we take a sample of a few people from the population. But again, the goal is that we're inferring, okay? We're making an educated guess using data. We're inferring about the population with information that comes from a representative sample, okay? So you'll notice that in this chapter of your textbook, they start talking about different types of notations or different types of symbols. And so at this point in the chapter, for the rest of the textbook, you will see different notations or symbols used depending on whether the information is coming from the population distribution or whether it's coming from a sample distribution. And so here's a little graphic table that shows you the different notations, the different symbols. So let's see if I can annotate this here. All right, so sample notation here. This is the symbol that we use to describe the mean from a sample. It's Y bar, right? We've talked about this before. And other textbooks you might have seen the sample mean called X bar. It's the same underlying concept. It's the mean from a sample. From now on out, though, you'll see your textbook showing you if they're talking about the mean from the whole population, they will use the Greek symbol here, mu. So this is mu. And so mu refers to the mean from a population and population distribution. And then we'll start seeing symbol for a proportion that comes from a sample as the lowercase letter p. The Greek letter pi here will be the symbol for a proportion from the population distribution. So this is pi. The symbol for the standard deviation from a sample here is the lowercase s. This here is the symbol for the standard deviation from a population distribution. And then this is the variance symbol, the s squared, and then this is the variance symbol from a population distribution. So it's important for you to understand and to be able to recognize these different symbols. It will make your life a lot easier if you memorize them, so that when you see them in the textbook from now on and when you see them in formulas that we'll start using, that you don't have to go back and look up what the heck is that symbol again. So it will make your life easier and things will go a lot smoother if you can remember what they are. All right. So parameter versus statistic. So any measure, whether it's a proportion or a mean or a standard deviation, if it comes from the population distribution, we're going to call it a parameter. Any measure that is describing information that comes from a sample distribution, we're going to call it a statistic. It could also be a mean, a standard deviation, a percentage, or a proportion. But if it's coming from a sample, we're calling it a statistic. If it's coming from a population, we're calling it a parameter. And the way to remember that is that the P's go together. So parameter comes from a population, and then the S's go together. So statistics come from samples. Okay, so here, sample notation and population notation again. So these symbols, okay, are all used for statistics. These symbols here, these are all used for parameters. So any information, any number, any statistic, excuse me, any number that comes from a population, we're calling it a parameter. Any number that comes from a sample, we're calling it a statistic. So here's another good visual graphic of what parameters and statistics are. So the population, the larger group of people here, and then we take a subset of them for our sample. If we're looking at the percentage of white respondents in a population, from the population, right, see we have down here at the bottom the pi. So the proportion of white respondents, white cases from the sample is 0.6. That would be about 60%. So in the whole population, right? About 60% of respondents are white. If we take a sample from the population and then we calculate the same proportion of respondents who are white, we'll see that about 0.67 or 67% of respondents in our sample are white. Okay, so your sample is a good approximation of the population, but it isn't perfectly just like this population. So there's going to be differences between your sample and your population. And so any number that comes from the population is a parameter. Any number that comes from the sample is called a statistic. And so now we'll talk about two important concepts, sampling error and sampling variation. So we'll talk about this like in the example of using the mean. So the sample mean that you're calculating is not going to be the exact same as the real population mean, right? The population is going to be much bigger than the sample is. And so when you're taking a subset, a smaller group from the population, a sample, you're not going to get all of the people that were in the population. And so there are going to be differences between the real population mean and the sample mean that you get. And the differences between your sample mean and the population mean, that's called sampling error. That's mistakes, right? Your sample mean does not perfectly match the population mean. There's some error there, some mistakes. The sampling variation is a different concept. That refers to taking multiple samples. And each time you take a different sample, you get a slightly different sample mean. Okay, and so that difference from one sample to another sample to another sample, that's called variation, right? Differences from one sample to another, sampling variation. Differences between the sample mean and the real population mean, that's sampling error. Sometimes you might read about in the media, newspapers, things like that, about something called statistical noise. So there is a certain amount of variation from one sample to another, and that variation is also called statistical noise. So going back here, okay, looking at this visual again. So we have the difference between the real population proportion of respondents who are white and the sample proportion of respondents who are white. So you see the difference there? 0.60, 60%, and 0.67, 67%. So there is a difference between the sample statistic of respondents who are white and the population's proportion or percentage of respondents who are white. And that difference is called sampling error. The sample does not perfectly match the population because it's impossible for it to perfectly match the population since it's much smaller. So the difference between your sample statistic and your population parameter is called sampling error. These are the technical definitions that you'll see described in your textbook. So sampling error is the difference between the sample mean and the real population mean. And you see here, this is y bar, the mean from a sample, and this is mu, the mean from all of your population cases, all of the y's. And so the mathematical definition of what sampling error is just subtracting the population mean from the sample mean. And sampling variation just refers to the sample mean differences from one sample mean to another. So next we're going to move on and talk about what probability or scientific sampling is. So probability sampling is the basis of pretty much all statistics. That you take a probability sample that is representative of your population, and then you can infer about the population based on data from your sample. So a probability sample refers to us selecting a sample that is as representative as we can get it to be of the population. And the way we select our sample is what allows us to make inferences. It allows us to generalize about the population based on data from our sample. The key features here, and there are two key features. First, that each case, if we're talking about our sample being people, each case in your population, each person in your population has an equal chance of being selected, being chosen to be in your sample. So if you have CSUN students, and we'll say that there's 40,000 students at CSUN, if that is our population, every student at CSUN has an equal chance of being selected to be in our sample. Okay? And then the other important part of probability sampling is that every possible combination of cases has an equal chance of being selected. And what that refers to is if we're taking a sample of 100 students from CSUN, that every different possible combination of 100 students out of the 40,000 in the population, that also has an equal chance of being selected. And so this is what makes it possible for us to generalize from our smaller sample to the much larger population, is that every person in your population has an equal chance of being chosen for the sample, and every possible different combination of people has an equal chance of being chosen for the sample. So not all samples that you'll see people using in research are probability samples. It's fairly common for researchers to use what's called a convenient sample. And so a convenient sample is kind of just like the name implies. It is a type of sample where the researcher chooses people to be in the sample because it was easy and convenient and accessible to the researcher. So convenient samples are non-probability samples. And so what that means is that everybody in the population didn't have an equal chance of being chosen to be in the sample. The only people who were chosen were people who are convenient for the researcher to access. And so a good example of a convenient sample is you want to study students at CSUN, but you can't easily take a probability sample, maybe because the university won't give you a list of all 40,000 students, and you can't randomly choose students off the list because you don't know who's a student at CSUN. And so what you do to get a sample of CSUN students is you go over to Oviatt Library and you stand out on the steps there and you hand out surveys to people as they walk into the library. And so that's an easy, convenient, accessible way of getting lots of students to take your survey at the same time. And that would be a convenient sample. It's not a probability sample because every student at CSUN, all 40,000 students, they were not at the library at that exact moment that you were there. And so they didn't have an equal chance of being selected to be in your sample. So convenient samples are fairly often used by researchers when they want to get a large sample, but they don't have the ability or the patience or the budget or the time to get a probability sample, okay? And so convenient samples have certain disadvantages that are widely known. So the advantages are pretty obvious. Just showing up at Oviatt Library doesn't take much time or effort on your part. You could probably get a survey sample of several hundred people in just a couple hours. And so it's easy, it's cheap, it takes less time than a probability sample would. The disadvantages, though, are pretty serious. The disadvantages are that your sample is probably not going to be an accurate representation of the CSUN student population, right? So if you show up to Oviatt Library, back before the pandemic, obviously, on like a Wednesday morning at 10 a.m. and you survey a few hundred people there, all of the people who are taking classes on Tuesday, Thursday, or on the weekend, they're not going to be at Oviatt Library on Wednesday morning. All of the students who take night classes, maybe because they work during the day, they're not going to be at Oviatt Library at 10 o'clock on Wednesday morning because they're at work. And so your sample isn't going to accurately represent the CSUN student population. It's just going to represent the people who showed up to the library at 10 a.m. and who are willing to take your sample. So the data that you get from your survey, even if you survey 500 people, even if you survey more than that, those data are not generalizable to the population. So you can't make inferences. You can't say, oh, I find that CSUN students think this, or they're like this, or they have this characteristic. You can't make that statement. You cannot generalize about the larger CSUN student population with a convenient sample. Your data only represent the group of people that you surveyed, and they don't apply to anybody else. So the most basic type of probability sample is what's called a simple random sample. And so here, every member of the population has an equal chance of being chosen for the sample, and all the different possible combinations of cases have an equal chance of being selected. And the classic example of a simple random sample is a lottery drawing. So if you've ever watched them do the lottery drawings on TV, they do them, I think, like once a week or so. And you have somebody like standing out on a stage with those like 3 plexiglass boxes full of little ping pong balls with a number on each ping pong ball. And then they pump air into the little plexiglass box so that the ping pong balls are spinning around. And that's, to make sure that all the numbers are mixed up well. And then they pull like a stopper out of a tube, and one of the little ping pong balls gets sucked in to the tube. And so that becomes like the first number in the lottery drawing. So the lottery drawing is a simple random sample, right? Another way of thinking about what a simple random sample is to think of, a bunch of names written down on a sheet of paper, and then we mix all of the names or the numbers up into a hat, and then we draw numbers out of that hat. So that is a simple random sample also. So how is probability sampling useful to us? So probability samples allow us to estimate the extent to which our findings are going to differ from what we would find if we had data on the whole population. So probability samples will have the ability to calculate what's called a margin of error or a standard error, which tells you how much error you have built into your sample compared to the real true population. And so if we use a probability sample, we can infer, we can generalize about the population. All right, so we've covered a lot of information here in this lecture. So we have a few practice questions to go over. So here are some practice questions. So we have a class of 23 people this summer. If we choose as our sample the first 6 people who log into Zoom, okay, and we make those 6 people our sample, is that a random sample? Is that a probability sample? So, and you should be able to explain why or why not. The next example is, what if we just ask for volunteers? So what if I just say, okay, who wants to be in my sample out of the class, and I take the first 6 people who volunteer? Is that a probability sample? And then the last example here is, what if I choose 6 people without a system? What if I just kind of look at all your faces in our Zoom class meeting and I just pick 6 people, okay? Is that a probability sample? So take a minute, think about this, these 3 different practice problems, maybe pause the lecture here and write out your explanation for, are these 6 people? Is this a random sample? Is this a probability sample? Why or why not? Okay. So first, choosing 6 people, the first 6 people who log into Zoom is not a random sample. So this is not a probability sample. And it's not a probability sample because everybody who is in the class did not have the opportunity to be selected to be in the sample. I just chose the people who logged in first. And so the people who logged in first might be different from everybody else in the class in some way. So this is not a probability sample. Choosing people who volunteer. This is also not a probability sample. It's not random. People who volunteer are, again, they're likely to be different from people who don't volunteer. The people who volunteer for things are often people who are outgoing, extroverted, talkative, sociable. And so those are the people who volunteer for things. And so what happens is if you ask for volunteers, what you get is a sample of people who are extroverted. And you miss all of the people who are introverted or the people who don't care enough to volunteer. And so this is not a probability sample. Choosing 6 people without a system is also not a probability sample. So if I'm just looking at all your beautiful faces in Zoom and just choosing 6 people that way, it's not a probability sample because I don't exactly know how or why I chose my sample. Maybe I was drawn to all of the people who have brown hair. Maybe I was drawn to all the people who are younger or all the people who are older or all the women. And so choosing people with what you think is not a system doesn't make something a random sample. It just means that you don't actually know how or why you chose them to be in your sample. So a true simple random sample for selecting students from our class would be to take all 23 people in our class. Everybody write each person's name down on a little sheet of paper, fold that piece of paper up, and then put all their names into a hat or a box or something, mix them all up really, really well, and then draw names out of the box. So draw 6 names out of the box or 6 names out of the hat. That would be a simple random sample. Everybody in our class would have an equal chance to be chosen because all of their names were in the hat. And if I mixed the names up well enough, then every different combination of students in our class would also have had an equal chance to be chosen to be in the sample. And so that's what makes it a probability sample. And so this is everything that I just said, just drawing numbers out of a hat. Okay, so here's some more practice problems. So this refers to the presidential debate way back in 2012, which is the debate between Barack Obama and Mitt Romney. This was Obama's second term. And so they're both running for president. Fox News LA conducts a poll on its Facebook page after the second presidential debate and asks people who won the debate, Obama or Romney. 7,000 people respond to their Facebook poll, and they say that Romney won the second debate. 1,400 people respond and said, no, 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 Obama won the debate. And so my question for you is this sample of 8,400 people, right, 7,000 plus 1,400, so 8,400 people, is that sample a probability sample? Why or why not? So pause, think about this, write out your answer in a few sentences so that you can explain yourself, and then you can move on to the rest of the lecture. So the Fox News LA poll is not a probability sample. because essentially what you have is a very large convenient sample. You have people who are volunteering to participate. And that's really what a poll is, right? It's in this case, a Facebook poll is people volunteering their answer. So whenever people are calling in to voice their opinion to a phone number or clicking on a poll within Facebook or something like that, it is never going to be a probability sample. It's always going to be a convenient sample. And so you have to think about who are the people who could have possibly taken this poll. First of all, everybody who's not on Facebook, they never even saw the poll. And so it's only a poll of people who are on Facebook, so Facebook members, and it's only a poll of people who were either watching Fox News at that time and knew that there was going to be a poll, or who had subscribed and were following the Fox News LA Facebook page. So everybody else who's a Facebook member who isn't following Fox News LA, or they weren't watching the Fox News LA TV show, they had no opportunity to even take the poll because they didn't know about it. Because political orientation affects now what news site we watch, where we go and source our news. That is also affecting the composition of the convenience sample. So Fox is known to be a channel and a media source that leans conservative, just like MSNBC is a news source that leans liberal. And so the people who are watching Fox News LA or who are following the Fox News LA Facebook page are likely to be more conservative than the general population of people who are going to vote in the presidential election are. And so this is not a representative sample of all voters or of all Americans. It's going to lean more conservative. And so that's probably also why you found that 7,000 people said that Romney won the presidential debate instead of Obama, because what you have is a sample of conservative people who are watching Fox News LA, who cared enough to go to their Facebook page and take a poll. All right, so here is another practice problem. So in the 1936 presidential election, the magazine of its day, Literary Digest, which is an extraordinarily popular magazine of the time, took a poll, and they asked people through the mail who they were planning on voting for in the upcoming presidential election. Was it Alf Landon or was it Franklin Roosevelt? So those are the two candidates for president. The magazine, obviously this is pre-internet, so everything is done over through mail, right, through snail mail. And so the magazine got its list of who it was going to sample through the government by getting lists of all the people who had registered their cars or who had telephones. So they have lists of car and phone owners from all across the United States. And they took a sample of 10 million names from that list. They mailed out a little survey through the mail, 10 million surveys out all over the United States, and they got 2.3 million people to return their survey back to them. Based on their survey of 2.3 million people, they showed in their poll that 57% of people favored Landon and 43% of people favored Roosevelt. The magazine Literary Digest predicts that Landon is going to win the election in a landslide. So my question for you is this a probability sample? Why or why not? So again, pause the lecture here, pause the recording, and think about this and be able to write out in a short paragraph your response. So here's the real election result. So the red states show that Roosevelt won the election, the electoral college in that state. Franklin Roosevelt was the Democratic candidate. And Alf Landon won the blue states. He was the Republican candidate in 1936. And so you can see here that Landon, in fact, did not win the election. There has not been a President Landon, but that Roosevelt won the election, and he won it by a landslide. Landon only claimed 2 states, Vermont and Maine, and Roosevelt swept every other state in the country. So how and why did the Literary Digest magazine poll get it so wrong? And the answer to that is that they took a sample of people who were car and phone owners in 1936, which was during the height of the Great Depression. And the people at that time who owned cars or who owned phones were people who were well off, probably middle class or rich people. And so all of the people who are going to vote in the election did not have a chance to be selected to be in the Literary Digest magazine sample. So inadvertently, the people at Literary Digest accidentally, they got a sample of rich people who own cars and who own phones in 1936. And what they really wanted, what they really intended to get was a sample of all voters who are going to vote in the election. But that's not what they did. So they got the wrong sample. And because they got the wrong sample, they predicted wrongly who was going to win the election. And so people who owned cars and phones back then were probably much more likely to be wealthy. And wealthy people, as we know, vote differently from people who are not wealthy. And so they showed correctly that wealthy people were going to vote for Landon, and they did vote for Landon. However, wealthy people made up a small percentage of the population. And everybody else in the country who is not wealthy voted for FDR, voted for Roosevelt. And so Roosevelt won the election. And so this is an example of how you can take a huge sample. So you can have a really large sample size, right? They had 2.3 million people in their sample, and they got it totally wrong because they took the wrong sample and they tried to generalize from a sample of wealthy people to the much larger population of all people who are voting. So they were generalizing from the wrong sample to the wrong population. And they just kind of got everything wrong here. So you can take a really large sample, but if you take a sample of the wrong group, right, where everybody doesn't have an equal chance of being selected, then you can't generalize to the larger population. So last practice question here. So every 10 years, you might have gotten a little postcard in the mail or letter in the mail in about 2 months ago in April. So every 10 years, the US Constitution mandates a census, a counting of the people living in the United States. And that's called the decennial US Census. And so every April, every 10 years, the US Census Bureau mails out postcards to everybody's home. And they ask you to fill out some basic information. This year was the first year that the census went online. So they sent you a little letter in the mail and asked you to log onto a website and take the census online. Prior to this year, they would mail you a postcard and you would just fill out the postcard and mail it back. So the decennial US Census is a count of everybody living in the United States in April 2020. So is this data collected by the census a population or is it a sample? And so you should be able to explain your answer in a few sentences. So pause here and write out your answer. So the answer is because the census is trying to count everybody living in the United States, the census is a population. It is not a sample. There are mistakes that are made in the sample. Some people are not counted because they don't return their postcard. Other people are accidentally counted twice, maybe because they filled out the survey twice. But just because there are mistakes within the sample where some people are missed or some people are double counted, that doesn't make the census a sample. Remember that a sample is a subset of the population. And what the US Census Bureau is trying to do is to actually count everyone in the population. So what a sample would have been in this example is if they tried to study a smaller number of people living in the United States. Okay, and so that's not what they're trying to do. They're actually trying to count up and survey everybody living in the United States. And I think there's something like 356 million or 7 million people in the US. So the US Census is a population, not a sample. So the moral of this story is it's not how many people that are in your sample that's most important. Remember, the Literary Digest people had 2.3 million people in their sample, and they still got it wrong. It's how you select the people to be in your sample, how they are chosen. So it's your sampling method that's important. And so what we want to do is we want to take a probability sample where everybody in the population has an equal chance of being selected to be in the sample, and where every different combination of cases or of people has an equal chance of being chosen for the sample. And so today you'll find that political polls are often able to accurately predict elections with samples of, say, 1,500 to 3,000 people. So you don't have to have a sample that is 10,000 or 15,000 or a million in order to be accurate. You just have to have a probability sample that is representative of the population that you're interested in studying. And that's it.